So now this is a new activity with a new open loop system dynamics, and this is much more complicated, and so we're going to see some interesting dynamics because of these two different set of complex poles. So definitely deviating from our second order system in this case. Our goal is to design a controller that has a step response that has a rise time less than 1 second and an overshoot less than 5%. And so we're going to take a look at that from looking using a proportional controller and then looking at it from a lead compensator perspective. So go ahead and give this a try, use the RL tool, spend some time adjusting the gains, and then in the lead compensator, the pole and zero locations to try to see if you can achieve a tight or reasonably tight design that accomplishes these time domain specs. As always, it's a good idea to evaluate these time domain specs in terms of the geometries in the complex plane. Again, because this is this fourth order system, it's not going to behave perfectly, but it's good to just kind of have these as a ballpark idea. And so these correspond to these time domain specifications. And what we're going to notice is that we have two zeros introduced by the open loop plant, and we also have two sets of complex poles. And so these are going to be very close to the origin, so they're going to be relatively slow. These are relatively faster, and they're farther away from the origin. And they also have more significant oscillation because the imaginary part is higher. So now let's go ahead and go into the RL tool, and then we'll come back and summarize. In order to start with the RL tool, I'm going to go ahead and plug in our transfer function, this complicated mess right here, and then put a 1 in for proportional control. And when I load that up, I get this for my RL tool. I've got the root locus on the left and the step response on the right. We have poles very close to the origin, and we also have these poles that start here and move upwards. And so as we reduce these, you can see that for proportional control, all we can do is slide along these values. And so what's going to happen is, as we're reducing these, this reduces the damping ratio, because that's going to push these, essentially the cone here, closer to the real axis, but it's also slowing the response down. So let's go ahead and get our design characteristics over here. So we're interested in the peak response, and we're also interested in the rise time. And so we'll get both of these up here. Try to find a way to see both of them. There we go. And so we are looking for an overshoot of at most 5% and a rise time that is 1 second. So we're doing okay with rise time, but our overshoot is too much. And so for that reason, we would try to push these down. So what you're noticing is that we are getting some strange behavior because we have such a complicated system. So this is definitely not a second order system. And so the correlation between our intuition is only kind of vague at this point. So again, we use these as directional indications. So one of the things that you're not really visualizing well because of the way the root locus is scaled is the fact that this Y scaling is so big compared to this X scaling. So the angle of the cone that we would use for this damping ratio is a little bit stretched. So that's part of the reason why it could be that these poles are the ones that are dominating the damping ratio. And so we may want to pull these further. And so what we're observing is that we're reducing the overshoot, and then it's increasing again. And so that what's happening there is that these poles are originally the ones that are determining the overshoot. And then at some point in time, we're decreasing them. It's decreasing, it's decreasing. And then right around here, you see that we come this overshoot is 13 at this point, and then it goes down to 12, and then back up to 13. And so what's happening is now these are the dominant poles that are causing the overshoot to be a large value. So what we're seeing is proportional control is not going to work in this case. So if we go ahead and do edit compensator and add in our lead compensator, then this gives us the opportunity to specify both a 0 and a pole location. And so we can see that what we'd really like to do is we'd like to get, so we need to keep this 0 location closer to the origin than this pole. And so one thing to see is just how this pole is affecting it. So what it's doing is it's pulling these two poles towards the left. And so pulling it towards the left then means that that is slowly helping that damping ratio. This 0 right here, you can see that it's not doing a whole lot on this side in between this 0, this blue 0, and this blue 0 of the plant. So we may consider moving it a little further away. And so we may consider doing this because that helps stretch this inner region. And then we may end up pulling this back as far as we want, perhaps a very long way, in order to pull these poles back. And so now it's a bit of a game to figure out exactly where this goes. So we're trying to find 5% overshoot. And so you can see now it's those. So again, here we're doing better. So these are the dominant poles right here. These are the dominant poles. So we've got a very large overshoot. We're going to be pulling these down, which is going to reduce that overshoot. We're getting lower and lower overshoot. We're doing well. So now we've gone all the way down to about 6%. And then at some point here, it's going to start going up. So right about here, it's going to start going up. And that's because if we were to zoom in, what's happening is that these poles closer to the origin are the ones that are going to end up starting to become the dominant poles. And so you can see that the effect of two different complex poles, because this step response has this extra peak to it. And so that's really due to the fast response and the slow response. And so you can actually kind of see that transition again right here, right about there, which is exactly where these poles trade off being the dominant poles. So these are the fast poles, this very small peak right here. These are the fast poles because they correspond to these closed loop poles that are out here with a negative, say about 12 real value. So it's going to be exponential minus 12. So it's going to happen very quickly. And if we were to reduce them, move this further back, then you can see that the peak is actually happening at those dominant poles out here at the fast response. But then once we bring this in here, now the peak is happening due to the slow response, and those are due to these poles that are closer in to the origin. So that's kind of telling us there's a fundamental limitation there. Right there at that exchange point is about as low as we can go. And so we're getting close here. We're doing just fine on our rise time. So we may consider pulling this back just a little bit further to see if we can move this point a little bit better. So that's going to give us a little bit more. And so we're maybe just going to need to keep pulling that back a little bit in order to help us finally get down to our value of 5. So we're getting real close, and that's about it right there. And so what we're seeing here is that we're able to achieve this overshoot criterion right here. Again, with a little bit more fiddling, you could probably get that to be a bit more exact. Here we haven't met the rise time very, very closely, but that's another opportunity for improving this particular control design with a bit more iteration. So we saw in the RL tool that proportional control was not able to achieve our time domain specifications. Essentially, the poles that followed along these arcs were trading off at some point with these, and that prohibited us from meeting our mainly our overshoot, but also difficult time meeting rise time. So this was not possible through proportional control, and then we took a look at using a lead compensator instead. The effect of the lead compensator with the pole all the way out here at a large negative value was to shift these asymptotes. So now instead of going this direction, these poles left in this direction. And so that gave an opportunity to have a a cone that essentially was closer into the to the real axis, which corresponds to a larger damping ratio and therefore a smaller overshoot. So that helped us achieve our overshoot. Again, we were seeing an exchange where essentially at some point in time, the poles that were located on this circle were becoming the dominant poles. So when they were here, those ended up being the dominant poles, and those were the ones that were dictating the overshoot quantity. So there was a trade-off point where we were jumping from dominant poles being here to dominant poles then being located out here. And so there was a trade-off, and that's kind of what helped us determine some values. In this case, I ultimately chose 0 in pole values here and a gain. And in this design, I meet the overshoot criterion exactly, but the rise time is actually faster than the requirement. It's possible that you could find a slightly better solution where you could yield a rise time that's a little bit closer and a slightly smaller gain, but that would be up to iterating through the design.